In topic 13, we'll learn how to solve second-order differential equations with constant coefficients when the characteristic equation has complex roots. So recall that in the previous topics, in topic 11, we had the case where the two roots are real and distinct. And in topic 12, the two roots are real and repeated. And for this topic, we have complex root. For this recording, I will be talking about complex numbers and Euler's formula, which will be useful for the study of solutions of differential equations. And then in the second recording for part B, we'll apply the formulas here to solve differential equations. So many of you may have seen complex numbers already, but here is a quick review. When we talk about complex number, we need to have the imaginary unit denoted by I, and it is the square root of -1. So then, if we squared I, we will have -1. But if we compute I cubed, then it will be I squared times I, and because I squared is -1, we will have negative I here. Similarly, I to the fourth will be, you could do I squared, and we get -1 square, which is 1. And I to the fifth, you can split into I to the fourth times I, and because I to the fourth is 1 as above, we have 1 times I, which is I, etc. Using the imaginary unit, we can rewrite square root of negative numbers using I. So for example, if we have square root of -4, then we may split as square root of 4 times square root of -1. And the square root of 4 is the usual square root. Because 4 is positive, we just have 2, and square root of -1 is I, we get 2i. Similarly, if we have minus square root of -4, then we do the same thing, and we get -2i. Another example, square root of say -12, then we may split as square root of 12 times square root of -1, and square root of 12 we can simplify as 2 square root of 3, and then we have I for square root of -1, etc. Now a complex number is a formula of the form a plus bi, where a and b are real numbers. This is called the standard form of a complex number. So for example, 2 plus 3i is a complex number, or negative 2 minus I is also another complex number, or minus 1 is a complex number as well, because minus 1 may be written as minus 1 plus 0 I. Now many properties of um, real numbers like associative, commutative, uh, distributive properties hold for complex number as well. So we could add, subtract, multiply, or divide complex numbers. But I will not focus on those over here. Now when we solve differential equations in the case of complex roots for the characteristic equation, we'll need to take exponential of a complex number. So next I will discuss what does it mean exponential e to the a plus bi. So first we need to define what it is. In general, for any complex number that denoted by z, we define e to the z as a power series, which you saw in calculus 2. In calculus 2, you only learned power series for real variable, but here we can use the same series for complex variable. So e to the z will be 1 plus z over 1 factorial plus z squared over 2 factorial plus z cubed over 3 factorial, z to the 4 over 4 factorial, etc. This is how we define e to the z for any complex number. And it turns out the properties of exponential hold. For example, if we look at a to the e to the 0, then you see that when z equals 0, you plug in here, everything is 0 except the first one, which is 1. So e to the 0 equal to 1, which is expected. And that's what you learn from college algebra. Another property is that we're not going to prove it, but it's also true, is that if we have e to the z plus w, then this can be written as e to the z times e to w. That is the rules of exponents that you learn in college algebra as well. Now, but here is an amazing formula called Euler formula that relate exponential with complex number to sine and cosine. So to see what Euler's formula is, let us look at e to the bi, where b is a real number. So by the formula, by the definition, we will have 1 plus b times I over 1 factorial plus b times I squared over 2 factorial plus b times I cubed over 3 factorial. Let me write out a few more terms. Plus b I to the 4th over 4 factorial plus b I to the 5th over 5 factorial plus b I to the 6th over 6 factorial, and so on. This goes on forever. But let's simplify. The first two terms we cannot simplify anymore, so just leave them like that. But the second one, we have bi squared becomes b squared times I squared. But what is I squared? Well, I squared -1. So we have that divided by 2 factorial. And then the next one is b cubed times I cubed. But what is I cubed? We saw it earlier. I cubed is minus I. And then b to the 4th times I to the 4th, which is 1. What about the next term? We have b to the 5th and then I to the 5th, which is I. And b to the 6th, I to the 6th is -1, etc. So after simplifying as above, we have in the series we have terms without I and terms with I. So terms without I are these. So let's rewrite those. Let's collect them into one group. So we have 1, and then the second one is minus b squared over 2 factorial and plus b to the 4th over 4 factorial, and then minus b to the 6th over 6 factorial. And you see the pattern. The next one would be what? Plus b to the 8 over 8 factorial. The next one would be minus b to the 10 over 10 factorial, etc. And we go on forever. And then have terms with I. These are the terms with I. So let us factor the I out like this. Then what left? For the first term over here, after we factor out I, we have b over 1 factorial. For the second one, after we factor out I, we have minus b cubed over 3 factorial. And you see the next one is b to the 5th over 5 factorial. And the next is minus b to the 7 over 7 factorial, etc. And this goes on forever. Now, again, recall another formula in calculus 2. actually two formulas. What does the first series represent? Does anyone remember that? It represents cosine of b. And what about the second formula? It represents sine of b. So we have showed Euler's formula, which says that e to the bi is related with trigonometric functions cosine b plus I sine b. Now similarly, if we do e to the minus bi, we could actually apply the above formula. Instead of b, we have minus b. So the formula above would give us cosine minus b plus I sine minus b. However, cosine is an even function, and you can see that from the power series, all the powers for cosine are even, so the minus would not affect the value. So we get the same cosine b. On the other hand, sine is an odd function, so minus will turn the value to minus. And we have minus I times sine of b. So the formula says that if we have a minus in front here, then it just the difference in the formula is that we have minus I sine b. Now if we put Euler's formula together with the property of exponential function, then we have e to the a plus bi is we split into e to the a times e to the bi, and e to the a is a real number, so e to the a is just the usual value real number times e to the bi. Euler's formula says that we have cosine b plus I sine of b. So together, let's just distribute it. We have e to the a cosine b plus I e to the a sine b. If instead we have a minus e to the a minus bi, then the same work above will show us that we have e to the a cosine b, and over here we have minus I e to the a sine b. So you see, whenever we have minus in front of the term with I, then we have the minus in front of the term with I here. So let's look at a few examples of how to use a formula. So simplify this. Say e to the I pi. Then by Euler formula, we will have cosine of pi plus I sine of pi. But cosine of pi is -1, and sine of pi is 0. So we have -1 plus I times 0, which is the same as -1. Another example, here we have e to the, say, 3x minus 2xi. Then what do we get? Well, we may use the formula above here because we have minus in front of the terms with I, so we may use this formula. For the term without I, we keep it at exponential, so we have e to the 3x. But for the term with I, we have cosine and sine. So first is the cosine of 2x, and then because of the minus, we have minus I, and again we have e to the 3x sine of 2x. Okay, now using exponential, uh, here we have exponential base e, but instead of base e, we may use other bases. And that example 2 here. Let's simplify. Say we want to simplify 2 to the pi I. How do we do this? Now this time, the base is 2, it's not e anymore. So we have to convert it into base e. And here is the general formula to convert from base, whatever base we have, to base e. So say the base is b, and we want to raise to a power complex number z. Then we could calculate taking natural log, then we will have, and then take exponential again. Then we have e to the z times log of b, natural log. So ln of b. This is the formula to convert between b and base e. And once we have base e, we may use Euler's formula. So 2 to the pi I will be e pi I log ln of 2. And so we may rewrite as e to the pi ln 2 I. And now we may use Euler formula. Recall that whenever we have e to the bi, it's going to be cosine b plus I sine b. So it's going to be cosine of pi log 2 plus I sine of pi log 2. Uh, we will not care about the exact values or the approximate value from a calculator. So you may leave the final answer like this. Now another example, say we have x to the 3 minus 2i. Then what do you think we get? There are two ways to do. The first way is to use the property of exponents. So we can split this x cubed times x to the negative 2i. Well, x cubed, we already know what it is, so we just leave like that. But for the second one, it involves complex exponent. So we need to rewrite into e to the power negative 2i ln of x. So here we are assuming that x is positive. So we may take log of x. Now by Euler formula, this with the minus sign. So it's gonna be cosine of 2 ln x minus I sine of 2 ln x. And we're distributing, we have x cubed cosine 2 ln x minus I x cubed sine of 2 ln x. That is the first way to do this problem. Another way to do is to use directly e raised to 3 minus 2i log of x. And for this, we need to distribute log of x into each of these components. We have e to the 3 log of x and minus 2 log x I. And now using the formulas above, this is the formula we need here. E to the a minus bi is e to the a cosine b minus I e to the a sine b. So then we have e to the 3 log x cosine of 2 log x minus I e to the 3 log x sine of 2 log x. And we may simplify this a little bit. We've done this before. E to the 3 log x, 3, we bring in the exponent and we cancel e and log. We get x cubed cosine of 2 log x minus I, the same thing as before. We have x cubed sine of 2 log x. And you see that this result here, this answer here, is exactly the same thing as the above. This is the end of this part A. Now for part B, which will be in the next video recording, I will discuss how to use the formulas here to solve differential equations.